Let us now see how we can use this torsion equation in practical situations. Let us imagine an automobile which is driven through the rear wheel. Here you see a engine driving a propeller shaft through the clutch and the gearbox. And let us say that the effective length of this propeller shaft here, which is connecting this end of the propeller shaft to this end, is 1.5 meters, and let the diameter of the propeller shaft be 50 mm. And then let us assume that the torque which is being transmitted is the torque which is being transmitted here is 2000 Newton meter, which you can call it as 2 kilonewton meter. It's a huge amount of torque for any engine, but we need to check it for the highest torque. Maybe when the vehicle is supposed to climb an incline, they drive through a first gear and through the reduction gears. So the speeds may be multiplied by almost 10 times. Sorry, the speed is reduced by 10 times, the torque is increased by 10 times. So therefore, maybe 200 Newton meter torque could be amplified to 2000 Newton meter torque. So let us expect that this shaft, whose length is 2 meters, whose diameter is 50 mm, is supposed to transmit a torque of 2000 Newton meter. So we can find out two things here in this situation. One is whether this shaft is safe and what is the angle of twist. So let us assume that for steel, the value of G, which is the rigidity modulus, is 80 GPa. So let us convert this 80 GPa into the regular unit so that it becomes easy for us later. 80 into 10 to the power of 9 Pascal. So that is 80 into 10 to the power of 9 Newton per meter square. And this is 80 into 10 to the power of 9 Newton. So 10 to the power of 3 millimeter whole square. So it becomes 80 into 10 to the power of 3 Newton per millimeter square. So 80 GPa is 80 into 10 to the power of 3 Newton per mm square. So we can find out two things in this problem. So given this value of torque, so let us first write down the equation for the torsion. So T by Jp is equal to tau by R is equal to G theta by L. So in this equation, the torque is given in the problem and Jp is given in terms of diameter. We know that Jp is nothing but pi d to the power of 4 divided by 32 for a circular shaft. So given the diameter here, we can find out Jp. So T is given in terms of Newton meter, it can be converted to millimeter, and we can find out the shear stress. But what is R? R is the radius at which suppose if I can draw the end view of this in a zoomed up way, so the shear stress is maximum at where R is maximum, that is where this R is the radius of the shaft. If the diameter is 50, the radius will be definitely 25 mm. So we need to substitute this R as 25 mm here to get the stress in the outermost fiber, which is the maximum stress in the system. Now let us find out the maximum shear stress here, which is present in the outermost surface, which is the radius R is equal to 25. So let us substitute the values. 20,000 Newton meter. So 1 meter is 10 to the power of 3 millimeter. So writing this is T, and Jp is pi divided by 32 d to the power of 4. D is 50 mm to the power of 4 is equal to tau which is the maximum value. So let me write it as tau max, because it is the maximum shear stress, because R is, I'm substituting as 25, which is the maximum value for R. So this is 25 mm. Now let us find out tau max. Tau max is equal to 2000 Newton into 10 to the power of 3 millimeter multiplied by, taking this onto the other side, 25 mm. This can be taken to the numerator, multiplied by 32 divided by pi divided by 50 mm to the power of 4. Now we see the units, that here it is mm to the power of 4, here it is mm into mm square. So this cancels out, and you finally get the unit as Newton per mm square, which is the unit for the shear stress. So let us now find out the answer here. So this is 2000 into 1000 into 25 into 32 divided by pi divided by 50 to the power of 4 is equal to 81.48. So the answer is 81.48 Newton per m square, and we know that this stress is within the half of the allowable stress. And you know that the allowable stress for most of the calculations, we take it as 250 Newton per mm square. So 250 divided by 2 is 125. So for most of the structural steels and the engineering materials, the shear stress should never exceed 125 Newton per mm square in most of the problems. So we have got the answer is 81.48, which means that this shaft, which is taking this huge torsion of 2000 Newton meter, is still safe, carrying a stress of 81.48. The same problem could be asked in a different way, where they would ask you that the shaft should not have a shear stress exceeding 82 or 81 Newton per mm square. So which means that in this problem, the value of tau is given, T is given, tau is given, Jp is given, you'll have to find out R. So in this way, so they can actually give you the value of R and then ask you to find out the tau in the outermost surface, or they would ask you to limit the shear stress in the outermost surface and then find out R. So one could be given and the other could be asked in this way. So in the same problem, the value of angle of twist could be found out, because we know T, we know Jp, we know G, we know L, so theta could be easily found out. So in this equation, we had earlier used this part, so now we will use this part. So we already solved for this. So T is 2000 Newton meter, Jp is pi by 32 50 mm to the power of 4. Then this is equal to G theta. G is nothing but 80 into 10 to the power of 3 Newton per mm square, multiplied by theta. This is in radians. The answer that you get is in radians, divided by L. L is actually 1.5 meters, which is 1500 mm. So we can actually find out for theta. So theta should be 2000 into 10 to the power of 3 multiplied by 1500 divided by 80 into 10 to the power of 3. So this will give you the value of theta. Of course, here I missed this value here, which I have to put it here. Pi divided by 32, which could be sent to the numerator, into 50 to the power of 4. So taking this, so 2000 multiplied by 1000 is again 3 zeros, multiplied by 1500 multiplied by 32 divided by 80,000 divided by pi divided by 50 to the power of 4 is equal to 0.061 radians. If you want the answer to be in degrees, you multiply this by 180 by pi, you get the answer as 3.5 degrees.